Okay, let's do a little review for the Unit 5 test on chemical reactions. Now, this test is going to include counting atoms, balancing equations with coefficients, identifying types of reactions, special considerations for combustion reactions, single replacement and the activity series, and double replacement and the solubility chart. For reference, you might want to have handy a periodic table and the reference tables that includes the solubility chart and the activity series. So what does it mean, counting atoms? Counting atoms, you did this on the Unit 5 review. This is where you had to figure out how many atoms there are in a formula or multiples of formulas. For example, in the first one here, there's 4 NAs, there's 4 Bs, and there's 16 H's. In the front, we call that a coefficient, and the little lower numbers are called subscripts. Remember that if you have parentheses and a 2 behind it, it means 2 of everything in that parentheses plus 6 times whatever that is. So how many O's, for example? Inside the parentheses, there's 4, and then that's taken twice, so that's 8, and then times 6 would give you 48 O's total in that situation. That's what we mean by counting atoms. Balancing with coefficients. There's a couple of ways this might look on the test. It could be a multiple choice question, and you have to identify one of the coefficients. For example, the correct coefficient for carbon dioxide in the following would be. So what you have to do is first balance the whole thing and then choose what would actually be in the spot for carbon dioxide. Once it's balanced, we would have these coefficients. If one is blank, that means that there's actually a 1 there. So to answer the question, the coefficient for carbon dioxide, then, your choice would be 3. Another type of question would be to have to put the coefficient for each thing in there. For example, here we ought to fill in the coefficients for each compound in there and put a number in the blank. After balancing, then, we have these coefficients. So to answer the question, blank number 1 would be a 2, a 3, 6, and a 1. Next, identifying types of reactions. Now, we considered these 5 types of reactions here: synthesis, decomposition, single and double replacement, and combustion reactions. Now, synthesis and decomposition are kind of opposites of each other. The keys here are that synthesis is always going to have just one product. So on the right-hand side, there's only one thing. There might be a coefficient in front of it, but only one compound. Decomposition has only one thing on the left. It might have a coefficient, but only one compound on the left. Single replacement is when a single element is going to replace part of a compound, and then the replaced compound or element will be all by itself. Double replacement occurs when we have a partner exchange, and parts of a compound will swap positions in that. So we have to have 2 compounds on each side of the reaction for there to be a double replacement reaction. Combustion reactions all have this similarity right here. It might be something different that's being combusted, but we always have O2 and 2 products, CO2 and H2O. Now, there is a certain case where if the supply of oxygen is limited, we may also make carbon monoxide. But as far as identifying chemical reactions, if it's combustion, it will show this much of the equation, and what is in the front could vary. The thing that's being combusted could be one of several hydrocarbons, compounds that contain carbon and hydrogen, probably one of these four here. Combustion. Now, combustion will have some special questions about the carbon monoxide issue. All right. Now, normally during combustion, you would make carbon dioxide and water. But if the supply of oxygen is limited, then you could be making carbon monoxide. All right, to remember, if the flame is blue, you're making carbon dioxide. If the flame is yellow, then you're making carbon monoxide. In actuality, you're probably making both at the same time. It may refer to this situation as having abundant oxygen, making carbon dioxide, and having insufficient oxygen, where you're making carbon monoxide. And that would be when you have a Bunsen burner and you adjust the air intake, and it would adjust the color of the flame. There may also be some questions about what causes carbon monoxide poisoning. The common causes are, faulty furnaces and things like that. And it may ask also, what are some of the symptoms of carbon monoxide poisoning? Headache, nausea, dizziness, shortness of breath, etc. Single replacement in the activities series. Now, on the review sheet that we have these sample problems here. And what we have to do is try to figure out if this happens or not. So we need the activity series, which is on your reference sheet, and just this part of the reference sheet is actually the activity series. So for each of these reactions, we have to first figure out if it will happen or not, and then see if we can figure out what the products will actually be. So for the first one here, then, we have copper, and it's going to try to replace iron. So then iron would be off by itself. Iron would be off by itself, not a Brinkelhoff, so I won't write Fe2. Now, the question is, can copper replace iron, Fe? Right, that's where the activity series comes in. We have to find copper on the chart. It's way down here. And iron, Fe, which is way up here. So copper is below iron, so copper cannot replace iron. So this would be a no reaction. We'll just write NR for that. Zinc. Can zinc replace iron? Zinc now is above iron, so it can replace it. So now the zinc will be connected to the nitrate, and the iron will be by itself, not a Brinkelhoff, so I won't write Fe2. Now, we may have to write the formula correct here. We would need a periodic table to figure out the oxidation number for zinc, and we look it up, and it's a 2+, only choice. And then the back part here is one of those polyatomic ions, and we could use this to figure out what that number is. Nitrate is NO3 with a 1 minus. NO3 with a 1 minus. So if I put those two together, I would have to write it as Zn NO3 taken twice. That would be the correct formula for that. Now, I think on the test is mostly multiple choice. You may not have to write out formulas like that. All right, that's what single replacement and the activity series is all about. It might end up being no reaction, or it might have a single replacement occur. Another thing we might need to look at about single replacement reactions is some lab data. That's what this chart was about. So on this chart, what we're looking at is a number of solids, and it's kind of fictitious elements or generic elements here. If we react them and try to replace these ions in a solution, then this is what the data is. So if I take a piece of solid element A and dip it into a beaker that contains B plus ions, I will get a reaction. And if I dip it into a beaker with C3 plus ions, I get a reaction, and in every case I get a reaction. For solid B, I get no reaction, and only one reaction. In solid C, I get 3 reactions, and solid D gives me 2 reactions, and solid E gives me no reactions at all. So the most reactive one, of course, is going to be the top one, solid A. The least reactive one will be solid E, because it did not have any reactions at all. Create an activity series going from the most to the least. So I'm going to put A on the top with 4 reactions, and then I'm going to put C with 3 reactions, then I'm going to put D with 2 reactions, and then I'm going to put B with 1 reaction, and then I'll put at the bottom E that had no reactions. So this is the activity series from these data, from the most reactive to the least reactive. Double replacement and the solubility chart. On the review, we have these few sample questions here, and it says use the solubility chart, which is this down here, to determine which of the 2 products are solid. Now, you could determine if the reaction happens or not based on the solubility of the products. If both products are aqueous, that is soluble, then no reaction would happen. If one or more of the products is solid, then the reaction will happen, and the solubility chart can tell you which one of them is going to be that solid precipitate. For example, in number 17 here, we have to figure out if BaCrO4 and NaCl are soluble or not. So we look at the chart. Ba, barium, so we find that on here. Here's barium right here. And CrO4 is, and you might need to look over here if you don't remember, chromate, CrO4, chromate. So that's this column right here. So barium chromate, is it going to be a solid? Then we have to look at the chart, and that intersection has an S. An S. Now S indicates solid precipitate. So barium chromate would be a solid. Now how about NaCl? Sodium. Sodium's way down here. And chloride. Chloride is this column here. So sodium chloride is aqueous. So that's not going to be the solid precipitate, but the barium chromate is. Now if we looked up barium nitrate, we would find that it's aqueous. All nitrates are. And silver chloride is a solid, so that will be your solid in that reaction. For the third one, we have Na2SO4. Now that would be sodium, and SO4. SO4 is sulfate. Sulfate, that's this column on the chart. All right, so we want to determine if sodium sulfate is aqueous. Aqueous, so that product is aqueous. All right, aluminum, CrO4. What is CrO4? CrO4 is chromate. Aluminum chromate. So then we have aluminum chromate. That is this right here. Aluminum chromate is a solid. So that reaction would happen. Now remember, if you end up with 2 products that are aqueous, then you would just say no reaction, and you would not have any products there. Even though you could predict what the products would be, no reaction would actually happen.